So thanks everyone for coming, and thanks for giving me the opportunity to kick off this summit with a talk that I hope will serve several purposes. First of all, I would like to give you a bit of an overview of the vision of Swarm. So we walk through the components. On the other hand, thank you. It's much better now, I guess. So, but at the same time, I would like to present a little bit novel and a little bit unrehearsed conceptualization of how Swarm is. Basically build it up from the ground, from most simple components, and give you a clear idea how the different modes and modules and components build on each other, and what constitutes as the core Swarm layer, and what products are layered on top of it. For the purposes of this talk, I mean the word communications in the broadest possible sense. So it includes in its scope quite a number of things, including publishing and consumption. So it's a bit broadly understood. The motivation that we got from when we building Web3 communications services is basically centered around censorship resistance and privacy. So the ideal situation is that when I present you with the particular services and how they are implemented or can be used in Swarm, the ideal approach would be to evaluate them in terms of their privacy and censorship resistance features, and we can focus on that, and some of these will be picked up and we go into details during workshops. So just to give you an overview in this talk. And of course we want to in the light of our motto with scalable, sustainable, and sovereign infrastructure, we obviously want to provide tools and communication services that give you sovereign ownership over the data that you produce, and sovereign right to grant access to that information. Host it on a scalable and cheap infrastructure, which allows for messaging services that we need to be autonomous, and also have it as a system which is economically sustainable through built-in incentives. And the incentives obviously ultimately connect this peer-to-peer technology with the Ethereum blockchain, which handles the consensus. So just to give you a crazy idea what the scope of this talk is. So I'm really aware that this is very ambitious, but this is basically what I'm claiming, that all these different things that you do on the web, the basic backend infrastructure that you need for that is coming in a fully decentralized and incentivized and secured way from Swarm. And hopefully I'm gonna show you how to build such things on Swarm. So as I mentioned, if you approach the communications modalities from the point of view of privacy and censorship, then these are the dimensions that you should evaluate them in. Whether and here as I say, communication is used in quite a broad sense. So when I say sender and recipient, which is the normal term used in the context of messaging, you can just substitute it with publisher, consumer in terms of consuming static content. So it's kind of the same thing. So in terms of the communication modalities, it's important to recognize how, like, what the relationship between the sender or publisher and the recipient and the consumer, whether the sender needs to know the recipient's identity, or what aspect of its identity is revealed to them. There's an important dimension I call imposition, which means that whether some communication modalities basically is forced on the recipient in a way. It's a bit like advertising, that it's put in your face even if you don't want it. If it's imposable, then basically if you have a public email address, for example, that's imposable in this sense, because you can just spam it with a message. You don't need to know the recipient, the sender, to get an email from them. So and also interactivity is very important. So to evaluate these different communication modalities in terms of their their required throughput and how much latency they tolerate typically, and in general what their efficiency metrics are, and most importantly, in general, in a continued setting of using a communication modality, how much information is leaked, and what information can be guaranteed to remain confidential. So let's move on to swarm components. These are the basic components or products that we currently advertise Swarm as, and that's what the components that we think Swarm comprises of. So let's go and build them up from ground up. So what is Swarm? So basically, a Swarm is just a bunch of nodes in a network, which all the assumption is that if they have some underlay connectivity protocol. In this case, it should be an authenticated, encrypted, multiplexed, framed stream, which in our case, historically, is the RLPX dev peer-to-peer protocol that the Ethereum is using, which runs under TCP/IP transport. There's a bit of a wink to Dimitri in the audience. The lib peer-to-peer could just replace this at some point or not. So this is basically, I consider this part to be outside Swarm a bit. So we can rely on that there's such an underlay network, but we don't consider as part of Swarm. So we have these nodes which can establish these semi-permanent connections or channels with the underlay connections, and they can connect. So the question is, what should they talk about, these nodes? Well, first of all they should talk about how they can organize an overlay network. So this is the Hive protocol. So first they organize themselves in the overlay network. What is an overlay network? Is when nodes generate some key which it defines their address in the overlay namespace. So this is basically the 32-byte or 256-bit integer address space, which we can define an XOR distance metric on it, and with this distance metric you can form a Kademlia topology. So Kademlia topology is basically a graph, a particular graph connectivity pattern, which guarantees some properties of graph traversal, namely that you can have a route between any two nodes, and the number of hops that you take is logarithmic to the size of the network. This is a very strong property, because this basically allows internode messaging with relays. So what we can do here is categorize the types of message relay strategies. So there's obviously one, the trivial one, when you just broadcast the messages to your peers. So now again, what you see in the graph here is the overlay network. So where I have the edges, these are underlay connections. So they are semi-permanent connections, and the connectivity pattern follows the Kademlia topology, which means that apart from gossip, which you can, where you in a particular area you just gossip and broadcast the message to all the other nodes, you can have efficient routing with relays, which we call forwarding Kademlia. This is central to the workings of Swarm, and it's important to notice that forwarding Kademlia allows basically makes message passing kind of sender anonymous, or at least it makes the sender plausibly deniable and difficult to get. But its recipient recipient is revealed, because that's what makes it efficiently routable. So this forwarding Kademlia, which now I indicate with the yellow arrows, that the message passing goes through several hops, is central to the workings of Swarm. So the other type of message passing modality is when we combine the Kademlia routing with gossip, which we call neighborhood addressing. Is basically when you do routing up to a certain neighborhood, and within the neighborhood you do gossip. And there's yet another modality which requires when you do message passing with forwarding Kademlia hops, then on each hop the nodes open a little ticket, so that they remember that something went through them, and they pass back the response. So basically we can define round trips with this forwarding Kademlia. It's also going to be very important later. So far so good. We have messaging and routing and neighborhood addressing with forwarding Kademlia. So we already have a component. We just stick an API to it and combine it with some encryption, clever encryption system. And what we have is basically PSS. So a node-to-node messaging system. So you can see a little table here. So in the case of if the overlay address of the recipients is fully disclosed, then you can have a direct routed message to one node to another. If the recipient's public key is known to the sender, then you can do encrypted messaging. If it's not known, then plain message. If the underlay address is only partially revealed or not revealed at all, if not revealed at all, then basically PSS gracefully falls back to Whisper, the original Whisper, which gossips the message, and it's picked up by the owner just by virtue of the owner being able to decrypt it with their public key. There's a special case on the right bottom corner when no public key is known or given, and there's a unencrypted PSS message sent to the neighborhood and gossiped around in the neighborhood. So this is used mainly for service messaging, so between nodes. So what does that mean? I will talk to you through it in the context of the next component. But first let's see what PSS can already be used for. It can be used for real-time chat, for notifications and service node messages. So these use cases are heavily used in Swarm. So here comes the storage layer. So it's not so far we've been concerned with a bunch of nodes that want to message each other, and they do the addressing because they want to look for another node. But in fact, in Swarm, there's other creatures that live in this network. It's not only the nodes, but it's actually data, and Swarm can be interpreted as a distributed chunk store, because these data are stored by the nodes that are closest to them. What does this mean? It means that chunks should have an address, and this address is meant to be interpreted in the same address space as the overlay address of nodes, which means that it makes sense to say that a certain chunk is stored with the node that's closest to them. So that's exactly how Swarm distributes the data. So far it's quite similar to DHTs in a way, but there's a very big difference, is that in DHTs normally it's information about a particular chunk that you find at the address of the closest node. Here in Swarm it's the actual data, and since the chunk size is fixed, and the hashing that determines the address of the chunks is uniform, or as long as these two properties hold, then we can guarantee that Swarm will be a load balanced storage over the nodes. And now you can see why this is important. So the Swarm also it's very important that when the chunks have to be retrieved or sent to the place where they belong, where they take in custody, then it's important that we validate that the chunks are valid, their integrity, because that means that you cannot spam the network with junk chunks. So it's very important that you have a scheme which is locally makes a chunk locally verifiable, and it's also very important assumption that once a chunk is always a chunk. So once you see the address of the chunk, then you know that you've seen it, and that's the chunk you've seen. There's no mutability from the chunk's perspective. So there are two ways to guarantee this. One is taking the content address. So basically, when the hash or when the address of the chunk really depends deterministically from the content of the data blob, this is done with hashing. So it's on the level of chunks, this is the chunk hash. But there's another tricky way, which is proof of origin. I will talk about this in a second. So, but first let's talk about BCC. So here as well. So I understand we talk about storage, and because nodes store the actual chunks that are close to them, but in fact using these chunks for anything is basically communication, because what you need to do is send the chunks to where they should be stored in the end, and maybe get back some receipt, some statement of custody, and for retrieval you also it's also a communication round trip, because you send a retrieve request and get delivered the chunk back. So these are exactly the types of message passing events which I told you that there's one modality where you see the round trip, like the forwarding and then back passing. So the examples for this are this storage and retrieval. So basically we can characterize it like this. So basically, so think of it as the timeline going from up to the bottom. So basically, the top node is the publisher. So it publishes a content which is the middle node, and that content is consumed by the nodes in the bottom. So this just illustrates that this type of publishing content is simply a one-to-many communication modality, and the two arrows just indicate to you that these are typically round trips. So the publisher publishes the content chunk to the neighborhood where it belongs and gets back a statement of custody, and the bottom nodes they send a retrieve request to the actual address of the chunk, which is picked up by the local node that stores it, which delivers the chunk to them which is the green arrows pointing down. So the important takeaway message is that with these cases we can cover all kinds of static content storage and delivery. So we can have blogs, websites, and apps. I'm cheating here because we're talking about chunks at the moment, and of course you need a layer where you can talk about files and sites, and I will touch on this in a second. But basically, when you retrieve a whole file or a collection, ultimately on the lower layer, this is what happens. So ultimately you request chunks from the swarm, and you upload chunks to the swarm when you consume and publish respectively. So, but one important message to take away is that since these publishing requests and consumption requests use the same forwarding Kademlia routing, it basically inherits some of these properties. So it basically means that you have anonymous publishing and anonymous consumption. So you can do anonymous browsing in a way. So just to add, how much time do I have? Thank you. So top it up with ACT. This is another component. So ACT basically adds a layer of access control over swarm chunks. It basically treats the encrypted contents. It has a method of distributing the decryption keys that encrypted chunks to particular grantees. And I don't want to go into the details. It's a very elegant solution how you can stick basically access control over content that's published in Swarm. I'm just mentioning this because the use cases will become clear. So when we talk, before I said that with the storage layer you can just have public depths or Wikipedia or any kind of blogs implemented. With the ACT put on, you can implement a restricted access forum, like you can have authenticated login area for a website. You can have a private group check history and all kinds of private sharing. So basically, you can create an ACT. An ACT stands for access control try. That doesn't matter. So you can create an access control structure that basically controls who you want to grant access to read your content, which is basically private sharing. So now we come to feeds, which is Javier's big work. I find this quite an interesting construct because it's so simple and yet so powerful. So feeds is used another modality to make sure that a chunk is immutable and locally verifiable. How does it do it? Instead of the chunk hash as a content address, it basically says that the address space is partitioned in a way that each user that has a public key has the right to occupy certain parts of the address space. So, for example, you can create an address from a topic and your public key hash together, and you have the right to occupy that part of the chunk space, given that you sign off on the content. And the assumption is that here is a very strong assumption is that it's by the swarm it's assumed to be kind of immutable or unique, because it's at the publisher, or in other words, it's at the publisher's discretion to double sign on a particular address, and therefore basically screw their own feed. But if they don't do that, because they are the ones that control the feed, then this can be guaranteed that for one particular feed address you have one particular content. And this is important because you can rely on the principle that once you see the address, you know what the chunk was, you know what the data was that belonged to that address. So what feeds do is basically bring a kind of temporal continuity to chunks. So what this means is that I just put it in a simple diagram like that. In that the top publisher node basically successively publishes content, and this is successively read by the consumers, and the feed addresses basically map some sort of temporal succession scheme or versioning or timestamps to parts of the address space, and therefore it can implement mutable content updates. So basically with feed you can track changing content. You can link together the unrelated content addresses of your changing, I don't know, website to one particular feed, and basically use the feeds to get the latest update or the history of a particular website, say. You can use it to update the database state, and you can use clever topic naming conventions to link feeds to certain relational information. So for example with feeds you can implement Facebook likes of a website, or you can publish upvotes for a particular post, or even comments on a particular post. And most importantly, the first one, this is in this list, they can implement a zero-link communication channel, because if two parties off-band agree, off-band on some other communication modality, they agree on a particular feed succession scheme. So feed succession scheme means that they agree that at any point in time they know what topic and name they use for looking up looking up a chunk, and they know what public key they use for the session, which public key can be completely ad hoc and not related to the public identity of the party you communicate with. This basically creates a zero-link communication channel. So what this means is that it's a bit like finding rendezvous points from the two nodes. That I put out a message here in this corner, and you later come and pick it up. We just have to know which part in the corner I put the message. And if we have a scheme that we agree that this morning I leave you the message here, and today in the afternoon I leave it to you at the door, then we can have some communication channel that way. So we're going to go into more detail about that in the messaging workshop, and I think Luis will talk about this scheme in much more detail, and hopefully we're going to have time to analyze a bit of the security and privacy properties in a bit more serious way for these communication modalities. But let's have this just as a teaser. So most importantly, the incentivization. So in this talk now I don't want to go into too much detail about the incentivization, but relating to how I introduce the workings of Swarm, incentivization should definitely focus on how we incentivize relaying, so message relaying, because that's central to how the network operates. And we have a solution to that, which is a peer-to-peer accounting system, where you can count service for service provision, and so service for service exchanges. So basically, when you pass me a chunk that I need, I credit you 1, and when I pass a chunk to you, then it's the other way around. So we equalize, and if the consumption and provision of a service is roughly equal on both parties, then they get away without too much exchange, so the value stays with the user. If the consumption tilts in some way, then there's a scheme to settle that with a kind of micropayment solution, basically with sending a check that you can cash in a checkbook contract. We're going to go into this in more detail, I think, in the context of Ralph's talk about the swapson and swindle framework later today, and I'm sure we're going to touch on this within the incentives workshop, which is also today. So we're going to talk a lot more about this in detail. But just the takeaway message is that very important that we have a very scalable, off-chain, cheap micropayment solution to incentivize relaying. That's the takeaway. And if that is solved, then basically we have the sustainable, scalable, and sovereign infrastructure for the communication, at least on the level of chunks, basically. So this is what I would call really the bare minimum, that the core of Swarm. If you have this, then this is basically the necessary network layer that can implement these network protocols. Then this can already go a long way. But let me continue with a bit more. So over chunks, there's also an extra layer. So you can interpret chunks as not completely independent of each other, but somehow assume that there's structural relationships over them. This is a whole new layer, which you can even think about this whole layer as application level. In actual fact, most of these solutions are brought to the core of Swarm, and therefore considered core part of it. But in effect, if you want to think of Swarm as just the chunk store and the chunk handling that I introduced so far, then you can think of it as some extra addition. So what's the general approach here? I only just realized this myself recently, how these things fit together. So bear with me. So basically, we had a talk with Elad Verbin in the Prague summit, where we presented this generic result, how the distributed chunk store can basically map and use to represent any functional data structure. So how does that work? So functional data structures are basically nodes and pointers, and you can turn them into distributed Merkleized data structures, which means that the nodes are serialized as chunks, and the pointers from a node to node is basically the chunk reference, or use the chunk hash, or if it's encrypted, then the encrypted reference as the pointer. And therefore you can immediately get to a Merkleized distributed data structure. Now, what this implies is that any query that you do by traversing this data structure. So, for example, think about a tree that you want to get to the leaf of, and you have to traverse the data structure along the branches of the nodes. So this process of traversal basically translates into successive retrievals of chunks, and and between the successive retrievals of chunks, you just interpret the canonical serialization of the node and see which of the pointers is it that you need in the next hop, in the next round of the traversal. So I give you use cases for this. Some of these already exist, and some of these I kind of should exist. So the swarm hash tree to represent files is already an existing example. So how we represent files in swarm is basically by building a Merkleized tree with intermediate nodes, just packing the hashes of their children. So it's basically a super simple representation of a tree using this distributed Merkleized structure. And when you retrieve a file or so when you retrieve something bigger than one chunk, this is exactly what happens in Swarm, that you basically take the root hash of the file, that's the file's address, and unpack it and see what are its children. You successfully retrieve them, and ultimately you get to the data chunks, and you have the file. The same happens on an even higher level when you organize files into directories or collections. This is how we do virtual hosting as well. So basically, this is how you represent websites on Swarm. So manifests are also this kind of data structure that you traverse according to certain rules, how you interpret chunks and how you want to traverse them. So when you retrieve a file from a directory, then you take the root manifest, interpret that chunk as a node in the functional data structure. You take the pointer, etc. So obviously, so the Ethereum state trie could be another example, which could be directly mapped. The Patricia trie directly mapped as a native data structure and so on. And another example I will not go into. And parallel to this, of course, the data structure operations they are valid. So random access to files is a typical example of the traversal operation. File retrieval through manifest, or when for example, when you want to get an account, a particular account through the Ethereum state, that's also a traversal over these data structures. The interesting thing about this interpretation is that if you have successive retrievals from through chunks interpreted as nodes in a functional data type, then actually traversing the queries by traversing can be interpreted as network protocols, and provable queries into data structures can be interpreted as forwarded requests, and on the way back they accumulate Merkle proofs. So it's basically outsourcing querying or traversal of a data structure. So one more point is aggregators. So aggregators is another concept where basically it's a kind of node where several sources publish to it, and it basically processes those input and performs some computation on them and publishes the result, and that result is consumed by several parties on the bottom layer. So this construct is basically using the same tools that we had before, feeds and PSS messaging. They can do the generic formulation of that is that obviously they need conflict-resistant data types, so that there's no consensus problem basically on updating a data structure, and therefore they can do simple things like indexing, aggregating, merging like timestamp indexes, or counting, and they can also be used in successive iterations to do some map-reduce operations, etc. So these are quite powerful constructs, and they could in principle be used now, because if you program the application logic, it's using basically the same lower level infrastructure as we have. Now, of course, these aggregators are typically ones that perform something that's not immediately seen. You don't immediately see the result. So it's kind of a promissory type of activity, which means that ideally it needs staking to be trustless. So if you have service provision by nodes without reputation, then you have to have provability or verifiability of their computation. This can be done with the swapser and swindle games, and aggregators can be used for various real life cases. So aggregators can be used to, for example, process, create an index for you for a public for a forum where polling the individual participants' feeds for their contribution does not scale. So, for example, think of a Reddit on Swarm. You typically will have the forum comments be indexed by an aggregator. It can also be used for offline mailboxing. A special use case with that is that I think we've hit upon that with Danny the other day, that when you have pinned content and when we implement pinned content, then when somebody doesn't find a particular content and there's an indication that there's a content maintainer who is responsible for having that content, then you can use this aggregator to notify them without them revealing their actual underlay or overlay address. So you basically can notify them through their public key. This is also a powerful use case. And of course, it can be used for counting likes and upvotes. So this is an important ingredient in a kind of social network context where you need aggregation of some result. So these are typical use cases which I would describe as multi-party updates to a database. So when we have to solve the problem that several parties want to update something, and we don't want to go to the blockchain to do that. Of course, when the computation is more complex and there's no conflict resistance data types possible, so there's a genuine transaction ordering problem or consensus problem, then you have to use the blockchain. Hello. So it's obvious. But you can also use it for very powerful things. I almost put Google on Swarm as the last point, but I changed it to full text search so that it sounds a bit less pompous. But basically, that's how you would accumulate a full text index over Swarm to basically chain these aggregators together. Okay. So just to wrap up, thank you. So the claim here is that Swarm can provide base layer infrastructure for communication modalities to be used in the Web3 context. In the Web3 context, it means that these modalities should be decentralized, incentivized, and secure. Basically, they should conform to the principles that we set out in our motto, that this infrastructure should be scalable, sustainable, and sovereign, and it's basically infrastructure that requires no middleman, and all the services allow low barrier of entry and participation for all. And the claim is that this is really, you can build it out of this very simple building blocks of Swarm, and hopefully we'll see the richness of such applications which use these kind of ideas in the future more and more often. So thank you very much for your attention.